Okay, so hello again, and let's go through the mark scheme for this set of questions. We have an additional helper this evening. So this is Button, the cat. Button! Hello! Hello! I'm helping. I'll have to kick him down in a minute because he's absolutely agony because he digs his little claws in when he's doing that thing where they paw you. But so if you can hear some sort of weird noise in the background, it's probably just him purring. Okay, here goes. So, question 1. In this question, you'll be assessed on using good English. Yeah, I ignore that because I know that just as soon as I get the science in there, I'll get the marks. Information in the box is about the properties of solids and gases. Solids have a fixed shape, are difficult to compress. Gases will spread out and fill the entire container. Ow! Go away. And are easy to compress. So, use your knowledge of kinetic theory to explain the information given in the box. I've got to consider the spacing of the particles, the moving of the particles, and the forces between the particles. So, as with any of these long answer questions, as I always say, it's all about making sure you've ticked all the boxes, isn't it? So, therefore, it's easiest again for me to put the mark scheme into the visualizer. So level 1, an attempt at a description of some advantages or disadvantages. Level 2, a basic description of wrong question. Try again. So for level 1, you're going to say something about either a solid or a gas. So one aspect of each, so you could potentially mention the spacing of the particles in a solid. That will give you a mark, or the spacing of the particles in a gas. For 2 marks, you just mention both a solid and a gas, and maybe the spacing of particles in a solid and the spacing of particles in a gas. Level 2, which is worth 3 to 4 marks, you would have mentioned both a solid and a gas and described more than one of these aspects. So if you said in a solid, the spacing of the particles is close together and they're not moving much, whereas in a gas, the spacing is very far apart and they're moving all over the place, that will give you 3 to 4 marks because you've mentioned both a solid and a gas, and you have talked about more than one of the points you should be considering. To be a level 3 though and get 5 to 6 marks, you just have to answer the entire question. So it says, using information in the box to explain this information. The information is about solids and gases, so you'd have to mention solids and gases and something about the spacing, movement and forces of them. So therefore you're going to say in a solid they have a fixed shape because the spacing of the particles is very close together and they are not moving very much. For example, you'll notice that I didn't just say something about each. What I did is that crucial thing that we've talked about quite a lot is I've done some linking. So I've linked this information to this information. So if you can link that information to that information and have mentioned something about solids, linking to this information to this information, gases, linking this information to this information, you're going to be 5 to 6 marks. Okay, question 2. So, a company is developing a system which can heat up and melt ice on roads in winter, and it's called energy storage. So during the summer, the black surface of the road will heat up in the sunshine. That energy is then going to be stored in the soil. Pipes are running underneath the soil, so I've got the sun's energy on the ground. There's a large amount of soil deep under the road surface. There are pipes running through the soil, and in the winter, cold water entering the pipes will end up warmer because of it being deep underground, and therefore it stays warmer. Those pipes then bring that water up to the surface, and that warmer water will melt the ice. The system could work well because the surface of the road is black, so therefore the black surface is a good absorber of infrared radiation. You get the mark just for radiation, in fact. What's meant by specific latent heat of fusion? So it's not just latent heat of fusion, it's specific latent heat of fusion. So latent heat of fusion will be the energy needed to change state from, so it's fusion, so therefore I'm going from a solid to a liquid or a liquid to a solid. So therefore melting wouldn't get me the mark because I'm fusing, so it's actually specifically going from a liquid to a solid. So specific latent heat of fusion though is specifically of 1 kilogram of it. So it's the energy needed to change the state of 1 kilogram specific latent heat of a substance from a solid to a liquid. So then I need to calculate the amount of energy needed to melt 1 kilogram, that's a good unit, I don't need to change it, of ice at 0 degrees C. They're giving me a temperature, but that's not important because the temperature doesn't change when a substance changes state. So specific latent heat of fusion of ice is that. So therefore this equation is given. It's not one we have to learn. So the energy to change state is mass times specific latent heat. So therefore the mass here is 15, the specific latent heat is 3.4 times 10 to the 5. So therefore the energy needed is 5.1 times 10 to the 6. You get all the marks for 5 times 10 to the 6. Another way to keep roads clear of ice is to spread salt on them. When salt's added to ice, the melting point of ice changes. A student investigated how the melting point of ice varies according to how much salt is added. And this is the diagram of the equipment that they used. So I've got a thermometer and some crushed ice in a beaker. The student added salt to the crushed ice to measure the temperature at which it melted. What would I need to control in this experiment? So the thing I would need to control is the mass of the ice, or I could say the volume of the ice, or I am allowed weight of the ice. The one word that we try to avoid, of course, is we do not use the word amount because that's not specific enough and it's often not allowed. During the investigation, the student stirred the crushed ice. Why? I need to tick 2 boxes. I'll give 2 reasons why I tick 2 boxes. The most likely reason people lose marks here is because they just tick 1 box. So, would stirring raise the melting point? No. Would it lower the melting point? No. Would it distribute the salt? Yes. Would it keep all the ice at the same temperature? Yes. Would it reduce the energy transfer from the surroundings to ice? No. So there, I've got it. The table below shows the data that the student obtained. Describe the pattern in the data. If I'm describing a pattern, I need an sentence. So therefore, the bigger the I don't know, the bigger something is, the something, gosh, I can't think of one on the top of my head, but here we go, let's do one for this. So the higher the amount of salt added, the lower the melting point. So I need to link the two together with an sentence, a comparison, a bigger, getting smaller, higher, lower. Those sorts of words is what I'm looking for. You would get the mark for a negative correlation. Correlation. As soon as I go under the visualizer, my ability to write completely disappears. Okay, so under soil electrical heating systems are used in greenhouses, which could also be used under a road, and then you put cables underneath the ground with an electric current going through them. So one greenhouse system has a power output of 0.5 kilowatts. I've got a kilowatt there. So if I'm going to do any calculations of that, I'd need to turn that into watts. Calculate the energy transfer in 2 minutes. So that's 120 seconds. So as soon as I start seeing that I've got a calculation coming up, the first thing I do is convert my units in the question. So calculating energy, so energy is power times time, so therefore it's a simple power times time, and therefore the energy transferred is 600,000. So what am I saying? 60,000 joules. So now I've got another 6 mark question, and in this question the local council wants to keep a particular section of the road clear of ice in the winter, and describing the advantage and disadvantage of keeping the road clear using those 3 things. So again, it's just one of those 6 markers where what am I doing? I've got to do advantages and disadvantages of all 3. So it's a classic one where I could do a table, I suppose, isn't it? But whatever I do, I have to make sure that I take each of them, so energy storages, and put advantages and disadvantages for it. Salt, advantages and disadvantages for it. Undersoil heating, advantages and disadvantages for it. So this is the one I got the mark scheme for, wasn't it? So therefore, level 1, some advantages or disadvantages are given. So you could just do all advantages or disadvantages here. There's a basic description of some advantages and or disadvantages for some of the methods, but to get all the marks I just have to put advantages and disadvantages of all methods. So therefore examples could be for energy storage, there's no fuel costs, there's no environmental effects, it's literally just a pipe under the ground with water being warmed up from the deeper soil. It is expensive to step and maintain, obviously, because you have to dig deep under the road to put the pipes under there, and it is dependent that in the summer you do get hot enough weather to warm it up, and digging up the earth is obviously going to destroy habitats. So to get all the marks you would only have to have maybe 1, 2, maybe an advantage and a disadvantage of each of them, and you get all 6 marks. Salt spreading is really easily available and cheap to do, but it can be damaging to trees, plants, drinking water, cars, and it would need to be cleaned away. Undersoil heating, which is one where we actually pass electrical current underground, isn't dependent on the weather. It can be switched on and off, so therefore it doesn't need to be there all the time. But it does cost a lot of money, obviously, because we're going to have to pass a current through it all the time, and of course it's bad for the environment because we're digging up which is the same, digging up the earth and disrupting those habitats. Okay, next. So this we should recognise, it's the required practical. So a student used the operation in figure 1 to obtain data needed to calculate the specific heat capacity of copper. So we've got our heater and our block of copper with a thermometer in it, a joule meter to measure how much energy is being transferred from the power supply. Then we're taking the initial temperature of the block, turning on the power supply. The energy transferred into the block is measured by the joule meter. The temperature of the block is recorded every minute, and the temperature increase calculated. And then this is how much the temperature increased. It's not actually the temperature, it's how much the temperature increased by. And then energy transferred, actually, which is the temperature, isn't it, in this case, because it's gone from 0. The energy transferred into the block is here. The energy is transferred through the block. What's the process by which the energy is transferred? So it's a solid, so it must be conduction. Use it, figure 2, to determine how much energy was needed to increase the temperature of the copper by 30 degrees. So 35 degrees. 35 degrees, I'm going to go across from 35 degrees and down to that axis down there, and then if I count across 1, 2, 3, 4, 5, 1, 2, yeah, it's halfway between, so therefore it is 35,000 joules. The copper block has a mass of 2 kilograms. Use your answer to part B, so this one here, to calculate the value given by this experiment for the specific heat capacity of copper. So first I'll write my equation. Let me just look back, I forgot to look at my units. So I've got kilograms there, degrees C, yeah, I'm fine. So the energy transferred is the mass times the specific heat capacity times the temperature change. So what do I know? I know the energy is 35,000. If you wrongly put a different number in, if you got the wrong answer there and transferred it over here but did everything else right, you could get the 3 marks as an error carried forward. So if this number's wrong, don't worry about it. As long as everything else you've done is the same as me, then you're fine for this part of the question. So mass was 2 kilograms, specific heat capacity is what I'm trying to find out, the temperature was changed by 35 degrees. So if you've rightly written in your number from here to 35, you've got yourself 1 mark. So then I'm going to do any maths I can do before I start moving it around. So 2 times 35 is 70 times the specific heat capacity. So therefore the specific heat capacity is 35,000 divided by 70, which is 500, which is my second mark, and joules per kilogram degrees C are the units. It's my final mark, and it does very specifically tell me to give a unit. Remember, if you can't remember the units, you can work them out from your equation, because when you're doing specific heat capacity, you did the energy divided by the mass times the temperature change. So it's the energy in joules divided by the mass in kilograms times the temperature change in degrees C. So this experiment doesn't give the correct value for specific heat capacity of copper. Why might that be? So the reasons tend to be because if you look back here, there is nothing around the copper block to prevent energy from being lost to the surroundings. So energy lost to surroundings. The other thing is that when you turn on the heater, you need energy to actually get the heater itself hot. There's another thing that you could mention. So energy needed to heat up the metal of the heater itself. Okay, great. So that's the end of that one, and I shall speak to you again in a couple of days.